Okay. So before break, we were discussing these activation functions that are core of your neural networks. Without these activation functions, neural networks cannot work. And we found out hyperbolic tangent, sigmoid, rectified linear units are the popular ones. And vanishing gradients is a problem, or exploding gradients problem is there, where waves becoming too small for computation or become negative, again, they cause problem in the piece. So sigmoid and hyperbolic tangent, also called as tan H, they suffer from exploding gradients or vanishing gradients. To overcome this, rectified linear unit is ReLU. So ReLU overcomes exploding or vanishing gradient problem. So if you are looking at ReLU, the default activation function. In most of the deep learning softwares, ReLU is the default activation function. So ReLU overcomes this problem. Now, one more activation function is there, softmax. Multinomial dependent variable. Right, when you're predicting more than 2, or multinomial predictions. Multinomial predictions. This is a softmax function, which is you have to use this function when you're predicting more than 2 predictions. So e to the power of zi sigma k is equal to sigma k z is equal to 1. Is equal to 1 e to the power of z is great. So basically what we are doing is k is your number of level, your classes in your dependent variable. K is equal to 1 means k is equal to 1, k is equal to 2, k is equal to 3, like that. We will have multiple classes in dependent variable. So zi by e to the power of zz. This is what softmax function is. So softmax function must be used for multinomial predictions. And most of the time we use deep learning for multinomial predictions only. For binary predictions, you can use ML. Deep learning does not work that well on binary predictions because they are designed to work on multinomial predictions, very large scale predictions. So softmax is a function which you need to use when you are dealing with multinomial predictions. So these are the prominent activation functions which you need to understand, which are widely used in deep learning. So step 3 is we are using sigmoid function here. Sigmoid activation in hidden neurons. So we are going to use sigmoid activation for calculation. That is the reason why I'm using it. So sigmoid of H1, which is sigmoid of what was H1? 1, right? Which is 1 by 1 plus e to the power of -1. If you solve this, it will be 0.731058. Sigmoid of H2, sigmoid of 1.3, 1 by 1 plus e to the power of minus 1.3. We'll get it as 0.785885. Sigmoid of H3, sigmoid of 0.8. 1 by 1 plus e to the power of minus 0.8, you will get 0.689974. So this is the sigmoid activation values. Step 4. Multiply sigmoids of hidden with output gates. Multiply the sigmoid of hidden with output gates, which is 0.731058 into 0.3 plus 0.78583 to 0.5 plus 0.68997 into 0.9. If you do this sum product, you get 1.2332121. Then step 5, sigmoid activation of output, which is sig of 1.2332 1 by 1 plus e to the power of minus 1.2332. You will get the value of 0.77438. This is probability. This is called probability. So the sigmoid calculations will generate probability. Remember sigmoid P. What is the output of logistic regression? Probability. P is equal to e to the power of, right, z divided by 1 plus e to the power of z. To take it down, 1 by 1 plus e to the power of minus z. Now, based on this probability, what is the classification rule? Classified as 1. Probability less than 0.50 will be classified as. So based on this, it will be class 1. But what is the actual class? Is 0. That means wrong prediction. So whenever neural networks predict wrongly, they start a process called backward propagation. Backward propagation is a process initiated when neural networks misclassify or mispredict. Right? What is backward propagation? Backward propagation is the process of adjusting all weights in the neural network such that the error is reduced. Backward propagation is process of adjusting all the weights. Here we have 9 weights. All 9 weights must be adjusted. You can't selectively select some weights and reduce them. No. All the 9 weights must be adjusted. and adjustment will be done iteratively. Adjustment must be done iteratively. That means using multiple iterations, you should reduce the error. Not doing it in one go. You have to do iteratively, multiple iterations. If there are lakhs and lakhs of weights, all the lakh weights must be, can't ignore one weight. That is the concept of backward propagation, derivative calculus and nuclear. The second thing in backward propagation at the adjustment of weights. In backward propagation, we need to adjust the weights, right? Adjustment of weights uses gradient descent algorithm. So gradient descent algorithm is what is used to reduce the. Now, if you are looking at what is this gradient descent algorithm, this is one of the popular algorithms within the derivative statistics, derivative calculus, gradient descent. So what you observe here? On the x-axis, you have the cost. This is the error or cost. This is the iterations. Now, the weight or the cost must be reduced in smaller proportion. The initial weight and the incremental step should be in smaller proportion. So what gradient descent algorithm says is reduce weight in smaller proportions over multiple iterations. Reduce the weights in smaller proportions over multiple iterations. And as you reach the, and there is something called local minima. You can't make the error zero. Again, this is also remember, see, it is not zero. You will only reach a local acceptable error. So there is always a local minimum cost, which you will target. We can't make it zero. In derivative calculus also, we can't make error. We have to reduce the error to a certain extent only, which is acceptable, which is your minimum cost, which will be greater than zero. The local minima is greater than, you can't make the error zero, right? It is only done above zero. And the weights must be done in smaller proportions over multiple incremental steps. As you reach your target, the weight also becomes smaller and smaller. As you reach your local minima, the error becomes smaller and smaller. Now, the question comes, why can't we reduce the weight in larger proportions? Some people say, okay, we can reduce weight in larger proportions also. You can do that, but there is a problem. If you tend to reduce the weight in larger proportions, this is what will happen. Okay. If you are reducing smaller proportions, you will stay on one side of the error. You will stay on one side of the error. If you tend to do it larger proportions, you will bounce on the both sides of the error. No, this is different. This is called learning rate. Learning rate is nothing but the weight adjustment rate. At what rate you want to adjust the weights. By default, weight adjustments in Python, TensorFlow, which you are going to use, is 0.01. You can give your learning rate also. If it is small data, we'll give 0.4, 0.05. Multiple learning rates we can give and do the grid search and get the best possible learning rate. So for fixing a learning rate also, we have to do grid search. This is the reason why we always go with smaller learning rate. You remember solver in Excel? How it does minimization, right? We used it in logistic regression, minimizing the error, minimizing the log loss, by adjusting the coefficients. It tries different iterations and finally it gives a solution. A lot of iterations will be done. Finally, you'll get it. In the left side bottom, you'll see it keeps on running the iterations. So this is the policy you should follow in neural network. Smaller learning rate or smaller adjustment weights should be done such that you will stay on one side of the error. Otherwise, you keep on bouncing like this, you will never reach your goal. So you want to reduce the error, but it is increasing the error. So the weight adjustment is also very important in the gradient descent algorithm. Now, there are new versions of gradient descent. One is stochastic gradient descent. Which we call it as SGD. We have Adam, which is the default nowadays in all meetings, which was faster. Adaptive momentum. Adaptive momentum gradient descent. Nowadays, it is the default because it runs fast. Adaptive momentum Adam. Right. So then you have Bayesians. Lot of work is being done on this gradient descent to make it even faster. So Adam is one which we widely use. Default. Adam is the default one because it runs fast. But it is an extended version of gradient descent. Solver also uses adaptive momentum. Solver also uses adaptive momentum. Because it runs very fast. 5-6 years back when we were running solver, it will take minutes. Now the same thing will be running seconds because of the adaptive momentum versions which are being used. So this plays a very important role in backward propagation. The solver, whichever you're going to use, how you do the weight adjustments, this all will be very important in the backward propagation. Okay. Now let us start the backward propagation. The backward propagation starts with calculation of error. Calculation of error, which is 0 minus 0.77438 is minus 0.7743, the probability. Right? Next, step 2, derivative of sigmoid. The derivative of sigmoid 1 by 1 plus e to the power of minus x is sigmoid of x multiplied by 1 minus sigmoid of x. Now this is the derivation. This is the derivative of sigmoid calculation. ds of x by dx, d by dx. So this is the derivation of the sigmoid. d by dx of 1 by 1 plus e to the power of minus x. So it is sigmoid of x multiplied by 1 minus sigmoid of, yeah, the derivative is sigmoid of x multiplied by 1 minus sigmoid of x. Okay. Now, step 3. Sorry, we are not calculated this part. So here sigmoid derivative 0.77438 into 1 minus 0.77438. We get an answer of 0.17155. Step 3. Multiply error with sigmoid derivative minus 0.77438 into 0.1747155. You'll get a value of minus 0.13529. Okay. Step 4. Divide step 3 with input sigmoids or thin-layer sigmoids. We will divide step 3 output with thin-layer sigmoids. That means minus 0.13529 divided by 0.731058 minus 0.13529 divided by 0.78583, comma, minus 0.13529 divided by 0.689974. That means you will get these three new values, which is minus 0.18506, minus 0.17216, minus 0.1960. These three, we call them as delta output. What do you mean by delta in mathematics? That means we need to deduct them from the original weight. So we will get actual output weight minus delta weight will give you new output. So actually 0.3 minus 0.18506, 0.5 minus 0.17216, 0.9 minus 0.1960. This will give you 0.1149. This will give you 0.3278. This will give you 0.703911. What we are trying to do? We are trying to reduce the weights or we are trying to increase the weight? What are we trying to do? We have to take negative weights only. The objective is to minimize the error, not to maximize the error. You have got an error, you need to minimize it. When you're doing an Excel, you have to do plus minus. You have to add the negative. So this is what minimizing the error, not maximizing the error. So these are the new output weights. In the next iteration, the neural network will replace the old output weights with this new output weights. Now, we have adjusted the output weights. Now we have to adjust the input weights. Again, we'll start the process. Divide step 3 in backward propagation. Original output weights. It is minus 0.13529 divided by 0.3 minus 0.13529. Divided by 0.5 minus 0.13529 divided by 0.9. Okay, so we get values as minus 0.4509 minus 0.2705 minus 0.1503 okay. So this is input weight adjustment. We'll start with step 3, which is the multiplication of error with sigma derivative divided by actual output weights. Then we will multiply multiply previous step with derivative of sigmoid of hidden layer, which means minus 0.45098 into 0.731058 into 1 minus 0.731058. Minus 0.27059 into 0.78583 into 1 minus 0.78583 minus 0.150329 into 0.68997 into 1 minus 0.68997. So you will get values as minus 0.0866 minus 0.0455 minus 0.03215. Right? Then divide the above values with input values or excess. This will give us the delta input weights. So what are input values? Both are one, right? That means same values will repeat 2 times. So the actual input weight minus delta input weight will give you the new input weight. So the first weight was 0.80 minus 0.08669 will give you 0.711. The second one is 0.20, 0.40, right? 0.40 minus 0.0455, you get it as 0.3544. The third one is 0.30 minus 0.032156. You get it as 0.26784. The 0.20 minus 0.08669. You get it as 0.11133 and 0.90 minus 0.04554. You get it as 0.8544. Last one is 0.50 minus 0.03215. You get it as 0.4678. So these are the new input weights. So we have done the first iteration of gradient, backward propagation gradient for this new weights. So we will replace these new weights with actual weights in the next iteration. We will do the same calculation and then we'll calculate the probability. If the probability is less than 0.50, it will stop there. So if the probability of 0.50 means the class will be. If the probability is again greater than 0.50, again it will start backward propagation. So when you are looking at neural networks, the iterations are very important. So how many times it should try to correct? I think in this max item is $200 MLP, multi-layer perceptron. The other name of neural networks is the scientific name of neural networks is multi-layer perceptron. Multi-layer perceptron, MLP. In Python SQL, we refer to it as MLP. MLP classifier and MLP regressor. Now, early stopping will also be there. If it reaches the goal, it will stop only. After 200 iterations, it could not correct, it will be there. Wrong prediction will be generated. So after 200 iterations, if it could not correct the error, it will generate it. If we do the error correction before 200 iterations, it will. So these iterations are very important. How many iterations you want a neural network to have for self-correction or self-learning? By default, it is 200. But in advanced neural networks, when you are doing deep learning, you can define. Based on the requirement and based on the data size, based on the computing size, you have to do the definition. And one more thing is, scaling of data is must. And preferably min-max scalar. Because it does not generate negative values, right? 0 to 1. So scaling is must. The numeric variables must be scaled for computational purposes. Faster calculations. You must not use standard scalar. You must use min-max scalar. Because min-max scalar will not generate negatives and zeros are given automatically. It will handle your vanishing gradient problem also very easily. So your vanishing gradient problem will be also avoided if you use min-max. Okay. So when you are looking at neural networks, this is a very important thing. So when you are looking at hyperparametric tuning, a number of hidden layers, there is no what to call fixed rule. You use great sets to find the get. Number of neurons per layer. Activation function. Learning rate. Optimizer. There is a gradient descent and all. Adam or SGD, whatever you want. You have to decide optimizer. And you also need to decide the loss function. Every algorithm has a loss function, right? OLS, ordinary least, maximum likelihood estimate, we try to minimize the loss function. So here also we have loss functions. Okay. Binary entropy, categorical cross entropy. So we have many loss functions which are there, but these two are commonly used. Binary for binary, categorical cross entropy for multinomial. So loss functions have to be defined. Iterations have to be defined. Iterations are also called as epochs. Epochs means one process of building the neural network and backward propagation. Feed forward plus backward propagation, one epoch or one iteration. Common terms, we use the word iteration, but in Deep learning, we use the word epoch. Epoch means feed forward building and backward propagating. That whole cycle, we call it as one iteration. That's what we did in the one iteration, which is called epoch. And the batch size also very important, particularly in image processing. Images have to be processed through batches. You can't push all of them in one go. 128 images, 256 images, your choice. Based on the images you are dealing with, so that batch will be pushed. Some batches of images will be pushed through the. So these are the common things which we need to adjust. And metrics are the same. MSC or mean square error or RMSE, accuracy for classification. So you can have these metrics. So these are the important parameters which you need to. And a basic neural network. But if you are going to advanced neural networks in image processing, there are other parameters also which you need to define. It can be MSC, error, absolute error, mean absolute percent error. If you mean square error, you have to do square process, get RMSC. So regression metrics are MSC, primarily MSC. And the root mean square. So this is the background theory of neural networks. Okay, so we'll implement this in, can do this whole calculation in Excel. So all of you open an Excel sheet. hidden layer neuron, which is sigma that is equal to sigma input n into weight n. Input into weight. Okay, so we'll calculate is equal to 1 into 0.8 plus 1 into 0.2. Similarly, is equal to 1 into 0.4 plus 1 into 0.9. Is equal to 1 into 0.3 plus 1 into 0.5. Input into weight. Okay. Sigma activation. One divided by 1 plus ext minus z. Is equal to 1 divided by 1 plus ext open bracket minus 1. Which is 0.73107. 1 divided by 1 plus ext open bracket minus divided by 1 plus sigma activation. Okay. Random output weights 0.3, 0.5, 0.9. Along with input weights, you will get output weights also. Is equal to 0.3759 into 0.3 plus 0.78 into 0.5, 68 into 0.9. This is your output value. Sigmoid output value 1 divided by 1 plus exp minus 0.7743. Actual output is 0. One by 1 plus e to the power of minus. Sigmoid is same, no? 1 by 1 plus e to the power of minus z. 1 by 1 plus e to the power of minus z. All right. So from this step onwards, backward propagation will start. So the first step in backward propagation is error is equal to 0 minus 0.77438. Oh, sorry. So sigma derivative, sigma of z into 1 minus sigma of z. All right. Then error into sigma derivative. Got it? Then divide column K with column D. Divide column K with column D. That means is equal to, it has to be fixed by pressing Fn by F4. Column K value is common. Divided by column D. Hidden sigmoids. So divide column K with column T. Column D is your hidden sigmoids. Okay. So what are this? Delta output weights, which must be minus from the actual output weights. So the new output weights will be is equal to 0.3 plus this okay. So we have done the new output weights. These are the new output weights, which will be replaced in the next iteration. Now, input weights. Divide column K with, hello, third floor reception में दे दो. So divide column K with column E is equal to, again fix it by pressing F4, divided by the original output weights. Okay. Multiply column n with derivative sigmoid column T. Is equal to minus 0.09 into open bracket 0.731059 into open bracket 1 minus 0.731059. Got it? So delta input weights will be this is equal to this, and you drag it down. Again is equal to this, you drag it down. Use is equal to, and select the cell. Drag down 3 cells. Then again is equal to, drag down again 2 times. Because we have to connect all the formulas so that we can use it again for the next iteration. New input weights is equal to actual input weights plus this. So drag it down. Control S. Actual weights, 0.8, 0.2, 0.8 less. Column B. Okay. Now we have completed iteration. So we got new input weights and new output weights. Now what I will do is I will copy this whole calculation. Control C. Give a cell gap, give a row gap, and go to home. Paste special formulas and number formatting. Paste special formulas and number formatting. Okay. Paste special formulas and number formatting. Now, what I'll do is I'll go to the previous iteration. First, copy the weights, Control C, paste special values and number formatting. Similarly, I'll go to the previous calculation, copy the new input weights, Control C, and then in the second iteration, paste special values and number. Now I have replaced the weights with the calculated weights. Now we got the probability of 0.69173. Error has reduced from 0.77 to 0.69. Now again, we got new output weights are calculated and new input weights are automatically calculated. So I will copy the calculation again. Second iteration calculation I'm copying. Control C. Give a row gap, paste special formulas and number formatting. Control S. Then I'll go to the previous iteration, get the new output weights, Control C. Replace it with the new weights. Paste special values and number formatting. I will also go to the previous calculation, calculate the new input weights, Control C. And in the third iteration, I'll replace them with paste special values and number format, Control S. Now the error came down to 0.59. So one more iteration, I think the error will come down to less than 0.50. Control C. Paste special formulas and number formatting, Control S. I'll go back to the previous calculation, get the new input weights, output weights, Control C. Go to the actual output weights, paste special values and number formatting. I'll go back to the previous iteration, Control C, the new input weights, paste them here, paste special values and number format, Control S. See? Now the probability is 0.48. Predicted output is 0. In fourth iteration, it got correct. So every time you paste the formulas and out of the calculation first, and then replace the values from the previous calculation. When you're pasting the values, paste them as values and number format.